Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. In this video, we're going to talk about bond polarity. We know that there are different types of chemical bonds, and they either can form by electron transfer or electron sharing. In one word, either is electron transfer or sharing is the distribution of the bonding electrons. Right? Depending on how evenly these bonding electrons are distributed between the two bonding atoms, we can call a chemical bond polar or nonpolar, and that's the bond polarity. A polar bond refers to a situation that the bonding electrons are shared unequally. On the other hand, a nonpolar bond refers to a situation that the bonding electrons are shared equally. Okay, so by this definition, an ionic bond is a polar bond. A covalent bond can be polar or nonpolar. If the covalent bond is made by the same non-metal atoms attached to the same groups, in other words, these two non-metal atoms are same and their environment are also same, the bond is a nonpolar covalent bond. All other covalent bonds are polar covalent bonds. When a covalent bond is nonpolar, we can use a polar arrow. It's an arrow with a bar on the tail pointing to where electron goes. So with this polar arrow, where it points to is which atom gets more electron than the other. Also, we can use a symbol delta plus and delta minus to indicate the distribution of electrons. The delta minus indicates where electron goes to, and delta plus means where electron goes from. Okay, so let's take a look at the example. Are the following bond polar or nonpolar? First, the bond in chlorine. Because for chlorine gas, it's only chlorine, right? So those bonding atoms are the same and it has the same environment, so it's a nonpolar covalent bond. Then how about water? The structure of the water is oxygen in the center and hydrogen on the side. Okay, does not matter what. The oxygen and hydrogen, the two bonding atoms are not same, so we call this a polar covalent bond. Okay, a very similar concept to bond polarity is a dipole moment. Bond polarity only tells you whether the bonding electrons are distributed equally or unequally, while the dipole moment is using a value to accurately describe how much polarity a bond is. So a dipole moment the symbol is mu, and the SI unit is dvi, or D, uppercase D. The dipole moment measures the polarity. So for a nonpolar bond, we say the dipole moment is 0, but for a polar bond, we say the dipole moment is larger than 0. The larger the value, the more polar the bond is. Okay, so with this, the concept of polarity and the dipole moment, we can rank the bond polarity based on the electron activity difference we talked about before. So we describe the electron activity difference of the ionic compound, the covalent compound with a polar bond, and a covalent compound with a nonpolar bond. As you can see, the larger the electron activity difference, the more the ionic character, which we would talk about before in previous video. But also the more ionic character, the larger the polarity of the bond is, and the more dipole moment is. So with that, if we ask you to rank the bond polarity, we can refer to the electron activity of the two bonding atoms. So for example, what is the sequence of the bond polarity among the following bonds? Carbon-carbon single bond, carbon-hydrogen single bond, nitrogen-hydrogen single bond, oxygen-hydrogen single bond, and selenium-hydrogen single bond. You may take out a spreadsheet and try to work it out by yourself first. Okay, so for this question, it asks the sequence of bond polarity, but in other words, because of the bond polarity and the electron activity difference relationship, we actually need to find out the electron activity difference between these two bonded atoms in each bond. Okay, and since we know the electron activity trend along the sequence, along the same row of the period, the electron activity increases. So carbon, nitrogen, and oxygen are in the same row, and the electron activity goes like carbon is smaller than nitrogen, which is smaller than oxygen. Okay, and along the same column in the periodic table, the electron activity decreases. So oxygen is larger than selenium, which is a few rows below oxygen. Okay, so because we have this trend of electron activity, you can tell if we don't look at the first carbon-carbon bond, that is a nonpolar bond, so the polarity is 0, that's the smallest. For the rest, all of these carbon, nitrogen, and oxygen are bonded to the same hydrogen. So if we see the electron activity of the carbon, nitrogen, and oxygen and selenium, we can find the electron activity difference of these elements with hydrogen bond. So it's CH bond is smaller than the NH bond is smaller than, which is smaller than the OH bond. And also OH bond is larger than the SEH bond. Okay, so then without even looking at the actual number of electron activity, we can have this trend like aligned. But in order to compare all of these 5 bonds, we do need to get the electron activity, especially selenium hydrogen, to see where it fits with the CH bond and NH bond. So we can have those values in the table, in the figure provided on the textbook, by the textbook, and then calculate the electron activity of all of these bonds. Just do subtraction. Okay, so the trend is actually the same as what we predicted. The electron activity difference between CH bond is 0.4, for NH bond is 0.9, and OH bond 1.4, so it's increasing. For selenium H bond, the electron activity difference there is 0.3, so it turns out to be even smaller than the CH bond. Then with that, we can rank the bond polarity as carbon-carbon bond, the smallest is nonpolar, and then SEH, then CH, NH, and OH with the increasing sequence. If we know the bond polarity of a single bond, then if we know the geometry of a molecule, we can predict the net polarity of a molecule, whether it's polar or nonpolar. So let's take a look at that. And when we talk about the polarity of a molecule, it can be 2D, it can be 3D model, so it takes up the spaces. So sometimes we need to use the 3D symmetry of polar bonds, or 3D symmetry of how this molecule looks like to determine the net polarity of a molecule. So I'm going to describe 2 scenarios here. So the first scenario are about 2 types of molecules. One is called trans molecule, the other is called cis molecule. So trans molecule means one type of atoms on different sides of carbon-carbon double bond, while cis means one type of atom on the same side of carbon-carbon double bond. I'll give you 2 examples. Here is the structure of trans 1,2-dichloroethane. And here is an example of cis 1,2-dichloroethane. Both of the molecules have a carbon-carbon double bond in the center. One carbon has 4 bonds. For each carbon, it has 2 extra bonds pointing up and pointing down. One of them pointing up, one of them pointing down. Okay, so for the trans molecule, for the left carbon, hydrogen is pointing up, chlorine is pointing down. And for the right carbon, chlorine is pointing up, hydrogen is pointing down. So if you draw the line along the carbon-carbon double bonds, the 2 hydrogens are on the both sides of the double bond line. But for the cis molecule, the left carbon has chlorine pointing up, hydrogen pointing down, while on the right carbon has chlorine pointing up, hydrogen pointing down. So they are the same. If you draw a line along the carbon-carbon double bond, both hydrogen are pointing on the same side of this line, and both chlorine are on the same side of the double-double bond line. So we call this situation cis molecule. For the trans and cis molecules, is actually a 2D molecule, which means all of these atoms are sitting in one plane. For each bond, we can determine the polarity of that. First, we have carbon-carbon double bond. For each carbon, it's attached to a hydrogen and chlorine. Okay, so these two carbons are the same type of atom, has the same environment. So this double bond is a non-polar bond. For carbon-hydrogen, well, it's not the same atom, so it's a polar bond. We can use a polar arrow to pointing from hydrogen to carbon. And for the same time, we can draw the polar arrow for another CH bond on the right side. These two polar arrows cancel out because it's the same bond and it's 180-degree opposite to each other, so they cancel out. And also for the CCl bond, chlorine is more electronegative, so we draw the polar arrow pointing from carbon to chlorine. And also we can draw the polar arrow for the other pair of CCl bond. So these two also cancel out perfectly with each other. So the net polarity of this trans 1,2-dichlorine ethene is 0, because the same pair of polar arrows cancel out perfectly. However, if we look at the cis molecule, draw a polar arrow for CH bond from carbon to chlorine on the left, and also for the right is also carbon to chlorine. These two polar arrows cannot cancel out. So the overall effect of this two polar arrows is pointing up. And if we draw the polar arrow for CH bond, like before, it's pointing from hydrogen to carbon, the net effect of these two CH bond is also pointing upward. So the net polarity of this molecule cannot be 0 because these polar arrows cannot cancel out perfectly. So the net dipole is not 0. So these two are examples of a trans and cis molecule. We also have molecules with a very high symmetry. For example, if we have the carbon tetrachloride, the overall geometry of this molecule is a tetrahedron. The 4 chlorine atoms sits in 4 vertices, while carbon is in the center of this tetrahedron. Oh, and sometimes when you see the structure like this, if you see the solid arrow, like solid triangle, that means the chlorine that it's attached to is pointing towards you from the screen. Well, if you see the dashed line between a carbon and hydrogen bond, that means the chlorine bond is pointing away from you to the back of the screen. So you can imagine this is a 3D molecule like this. Okay, but if we draw the polar arrow for each of this bond, obviously the chlorine has more electronegativity. So we draw a bond polar bond from carbon to chlorine, and that will apply to all of these carbon-chlorine bonds. And because this molecule is so symmetric, these 4 bonds will cancel out in the 3D world. Okay, and because these 4 bonds cancel out, the net dipole moment is 0 for this carbon tetrachloride molecule. However, if we replace some of them, if we replace 2 of this chloride with hydrogen, so now we have the dichloromethane. We can also draw the polar arrow from carbon to chlorine. These 2 carbon-chlorine polar arrows will have a net effect pointing towards the right top corner. However, it will not cancel out with the other 2 pairs of the polarity of the CH bond. So for that, all of these pairs of dipole moment cannot cancel out, so net dipole moment is not 0. So for this molecule, it's no longer a perfect tetrahedron. Okay, so it's a molecule does not have this high symmetry. So the net dipole moment is not 0. All right, this is end of this video, and I see you next time.